Okay, thank you so much for invitation and give me the opportunity to talk in this amazing meeting. I'm going to talk about the detectability of gamma ray burst optical prompt and afterglow with Iranian National Observatory. Actually, my main goal is to introduce this new telescope that I would like to infer you to this science news, which comes back to 19 October 2022. The title is "The Door is Open. Iranian astronomers seek collaborations for their new world-class telescope." Yes, this is the things that I'm going to talk about this new instrument, which is in let's say some unique region to cover the telescope coverage around the globe. And in the first part of my talk, I will try to give you some overall picture about this instrument and the capability of this instrument. And in the second part of my talk, I will try to give some hints about what we are doing now, along with observing these transient events, including the gamma ray burst. I put a part of the this science news here. You can see it is written that in building INO is a short name of Iranian National Observatory. In building INO, there was, you know about this, there was so much sanctions about the high-tech import, and also there are some visa restrictions for traveling of astronomers around. This is also including me, because the reason that I couldn't come to this meeting is exactly related to this visa limitation, that I couldn't get my visa up to now. So, including all of this, the Iranian astronomers working like hell to build such an amazing instrument. Except the glass that we bought from Germany, all of the things built from the scratch by the Iranian astronomers. I mean, we should even construct some instrument to construct some other instrument. This is the things that has been done over the past 2 decades. Here you can see why this is very important, because you can see the distribution of the optical telescope all over the globe. And here you can see there is a gap exactly in the Middle East, where for sure we need a continuous coverage of the optical telescope, especially for follow-up observation of the transient sources. And you can see this is the only operative telescope which in this region, which is a 3.4 meter telescope in Iranian National Observatory. Here you can see also we have a telescope of the Turkey, which is a 4 meter class telescope, and also another one which is 3.6 meter in India, which both of these telescopes, as far as I know, is passing the last stage of the construction. So you can see that the importance of having this instrument to have a continuous network of the optical telescopes. So here you can see some timeline for a construction. Actually, this idea started at some around 2000, and you can see there was a site selection which started from 2000 and it's finished up to 2007. And then the conceptual design started, the constructing the road making the heel to host this instrument, and this was, let's say, finished up to 2016. And from the 2016 to 2021, there was a construction of the main building and the main dome, and the first light was obtained last year. Here you can see the 4-meter class telescopes. Of course, we have also some more huge telescopes which are coming. One of them is the Rubin or Vera Rubin telescope, which we have here some talks in this meeting about that. What you can see here also, ENO is among these 4-meter class telescopes, and this can help us to have some more valuable information about this transient sky or other sources that can be explored by this kind of telescopes. You can see there are thousands of the pieces to join together as a whole to have this modern telescope. And this telescope is in class of Ritchie-Chrétien, and the wavelength coverage you can see is 325 to 2500 nanometer, and the main mirrors has a 3.4 meter size, and the field of view is something like between 8 to 20 arc minutes, and the tracking is something like 0.2 arc second, and this telescope is working based on the alt-az system. So if I give you some hint about the instrumentation, this telescope passed the phase 1, and actually I can tell you this is at the end of the commissioning phase, and we got the first light last year, which I will show you some let's say engineering images about this telescope. And what we are doing now is doing some scientific project as well as doing this commissioning phase to complete the instrument and test everything about the control system, about the imaging, about the software programming, and design the instrument for the scientific goals. And what we have now is the imaging camera, which has a field of view around 4 arc minutes, and also a low resolution spectrograph will be installed to the telescope, I guess, around the spring. And here you can see the phase 3 of the telescope, which having a imaging camera, which field of view around 20 arc minute, and also a high resolution spectrograph. In order to give you some because I feel some quiet, just I would like to check if everything goes well. Just if Fabian can tell me a word, or someone else. Okay, great. So good. So here, just I would like to show you a short movie about this telescope. You can see this is actually at the top of a mountain, Gargash, which is around 5,000 kilometer, 5,000 meter up to sea level. And this is one of the highest mountain in Iran. And it is exactly at the center of the Iran. with something like 200 days a clean sky for seeing. And this telescope is using active optics, which is the modern facilities for the modern telescopes. And this telescope is designed based on the let's say the dome is somehow a dead building. This means the observer is not inside the dome, and everything is doing remotely, and the observer site is next to these telescopes, and during the observation there is no one inside the telescope. And since we are living in a dry region, we are somehow benefiting from so many clean sky during the year. And yes, this is the view of the telescope and also the other instruments, the hydrodynamical lift, and also other. This is also a real image of the Milky Way from the telescope side. So for more information and also about looking at the scientific goals of these telescopes, so you can refer to this website, which is the main website of the telescope. And here is the first light of the telescope in 2021. Here you can see we could reach to the image quality of 0.8 arc-second, which was amazing for the first experience to construct this kind of modern telescope in Iran. And here you can see in the right side also we have another image of NGC 23, which has some 0.65 arc-second resolution. And here also you can see the other image, and actually the scientific and engineering team take care, deep breath after seeing this image, to see this 2 decades effort finally lead to success. But the point is, the game is not finished. We just entered to the party, and this is one of my goal to present this talk here, because we are looking forward for the international collaboration, and this is the stage that I can present the potential of this instrument and invite you to send your proposals for whether follow-up observations or in each stage of the collaboration. Here you can see some insight about the control system and software development. Actually, this the right image, the right top image, is about the control room, which was next to the main building. And here you can see some of the softwares that are developed for the tracking system, for the focus staff, and for the collecting the data, and etc. And here also you can see some other user interface of the telescope. We have also a lens array, a Canon lens array in the site of telescope. And this lens array, you can see, is some 3 Canon lens, which of course are large field of view, around 154 times 116 arc minute, which is around, let's say, some degrees. And this also helped us to have some follow-up observation, as well as looking at deep sky for low brightness sources to in our scientific task. So let's come to the science project that we are going to study with these telescopes. And you can see this can be divided to the galactic and extragalactic sources. In the galactic case, we could look for exoplanets, micro lensing, the solar system, and also in the side of the galaxy, we could look at the star forming region. We could look at the gravitational lensing, active galactic nuclei, quasars, and also the gamma ray burst that I'm going to talk more about it. And we have some operation modes. You can see this is divided to the regular observing times and also the survey programs. And we are following this open sky policy. So let's come back to the title, which was about the detection of the gamma ray bursts. The gamma ray bursts are among the amazing extragalactic sources that we have a large event rate for them. For example, you can see that we normally observe something like 2 or 3 gamma ray bursts per week by the satellites. And of course, the rate is different for the long and short gamma ray bursts. And we have here so far during this meeting some talks about the gamma ray bursts. And I won't go to much more detail about this event rate. But the important point is around, let's say, 50% and less than 50% of these sources has optical counterpart. And this is very important for ground-based telescope to define some essential criteria for follow-up observation. And this is one of the one of our ongoing projects, which we are trying to define some essential criteria for GRBs based on our facilities, based on our instruments, and based on, let's say, also our chance to see if we have the chance to observe one of them before that goes below our threshold of observing or go outside of our visibility region. So here you can see some of the analysis that we have done in order to see this is all of the Fermi GBM sources, and we consider the those sources that we could observe that in principle, and we try to consider the fluence and the and also to see if we have some let's say some essentials for observing those that observed already by the ground-based telescope. You have heard also about the gamma ray coordinate network. But the important point about the optical telescope is measuring the fluence and also the fluence in the optical bounds. We always define a magnitude for our sources, and we know in the case of gamma ray burst, this magnitude goes below the threshold after some few days. This relation that I showed you in the above the page shows the evolution of the magnitude of the gamma ray burst, and always the afterglow scales with the power law timing, some T2 minus alpha. And this alpha is some value between 0.4 and 1.4. And here you can see some example of this, of some GRBs in which you can see in different filters the magnitude is started, for example, from 18, and it goes down up to 24 after a few days and a week. And this shows us normally we have less than a week or just a few days and few hours to observe one of these sources with the ground-based telescope, especially in the case of afterglow. For the prompt emission, we have we need a fraction of the second. So it seems that I'm going to, and okay, since I have not so much time, I have to go a bit faster. Here you can see, for example, the GRB 14081A, and this is observation timelines, and about in the case of the optical, so far we have just a few cases observing the prompt emission, and as I mentioned, we have almost 40% of the GRBs to be able to observe them in the optical region for the afterglow part. And but it is important to check how we can define the criteria that I mentioned. For example, if there is a source in China detected by some telescope, this is very important. I think this is the main task or the main goal of the software or apps like Colibri, because this is somehow you build these apps to inform the people, to be aware, to connect to each other, and this is very important to not mix up with so much information. Just as I can say, already there are too much information inside this app, and I would like to ask, don't make it complicated by adding non-essential information. But I would like to say some, I would like to give some suggestions for these apps. For example, something that are very important for astronomers to for follow-up observation, especially in the side of the optical follow-up observation of the gamma ray burst. Usually, as an astronomers, it is essential for us to have a field of view image for the sources. That would be great, because some of the ground-based telescopes give this field of view image, but it is actually a very hard task to find which one of them gives this image. And another point that is very important for an observer is the magnitude predictions. This is to estimate that, especially in the case of afterglow, is there enough time for the observer to catch the source? And also, another point that would be important is the most precise localization, because when there are several ground-based telescopes observing a source, usually it's a hard task to find the most precise location or localization of the source. That would be great if there are some somehow a way to find this most precise location. Or maybe make a community for networking the people, like a social media. That was the things that mentioned with one of the speakers about the connection of the brokers and astronomers around the scientific project and to follow up observations. And this is just some meeting that we did previously in our university. And thank you for attention, and sorry if I went a bit out of time.